Hi everybody. Today we discuss the hardware of the 688012, and this is the main issue covered in chapter 5. So pretty much we will only have an overview of the hardware structures. So we will introduce everybody to the 688012 hardware system first. Then we will discuss its operation mode. So it's called the mode of 688012 microcontroller operation. Okay. Then we will talk about its hardware pin assignment. And so when the 688012 works out, we have some external hardware pins, and we will talk about that. Then we go to the individual subsystems, and we will focus on the register block and port systems. So before we go to the details about the hardware subsystems, and then let's refresh our mind about the hardware systems we discussed at the beginning of the semester. Remember, at the very beginning of the semester, and we mentioned the 688012 is a 16-bit CPU. Okay, it's a 16-bit microprocessor. So the data bus is 16 bits. Okay. Yes. However, the way we program is very similar, is very identical to its previous version, to the 68HC11. So the programming model is pretty much very identical. Okay. So any program we developed with the 68HC11 can still work, okay, with 68HC12, okay, without any change. So okay, and we discussed the main difference between these two versions, between the 68HC12 and the 68HC11, is about speed. And while 68HC12 has data bus 16 bits, while 68HC12 only has 11. And the 68HC12 has much more pins and has much more port systems than 68HC11. Okay, because it developed for much more powerful or high-speed processing. Data bus and CPU, okay, is double speed. Now also 68H12 has a much richer instruction set. We mentioned it has 209 different instructions, okay, which is much larger in comparison to the 68HC11. So it's much more powerful and also flexible, designed for various types of applications. And even though it's the same microcontroller, but the 68H12 designed in different versions, or we call it what is designed to operate in different variants. Okay, so we have A4 version, and we have A0 and A4 and B32. So pretty much we talk a lot about A4 and B32, especially we are more interested in A4. But no matter which version we talk about, no matter which variant, all of them run 16-bit microprocessor. Okay, on all of them, okay, it consists of a series of modules, okay, that are connected by an inter-module bus called a LIM. So this one shows like a module, but serves as a bus. So all different components, all different subsystems, they're connected into this module. So lighter integration module, LIM. So they run pretty much the same microprocessor, but what's the main difference? Okay, what's the main difference between them? Main difference is what? Okay, it's about what? It's about the size memory we configured. Okay, here we mentioned the different size of EEPROM size, flash RAM size, a number of input-output ports, because they're designed for different applications. Okay, so in some application we require more channels. In some application we require fewer channels, or for some application we require more output channels. For some application we require more input channels. So they're different. And also the communication port configuration also different, depends on which version we use. And our discussion focused on A4, as I mentioned way at the beginning of the semester. So I mentioned about all of them, all of the 3 variants. Okay, the many connected word into the LRM. Here I show you. So in this slide, what I show you is the block diagram of the A4 version. Okay, this is what for A4 version. Okay, this is the one we focus on. So and we saw this before, and this one is given in this block diagram is showed in I think in chapter 1, and also is what is shown again in chapter 5. So here it shows us about what for the 6080H12 A4 version. Okay, how the block diagram look like. It's pretty much something like this. So we see the main module right here is like this, is LRM. This shows like what integration bus module. Okay, you see all components that are connected into this module. So this one shows pretty much like a bus. So we have here, we have the RAM here, memory size RAM. We have EEPROM is 4K here. We have CPU systems, this microprocessor, and then we have what? And we have time clock systems, time clock interrupt systems. We have what? The timer systems, ADD conversion, and the serial communication, and serial peripheral interface, different systems. And we all have different ports. Those are ports. They're all connected into this bus. Yeah, like this. So for B32, I want you guys to take a look at by yourself. It's shown on page. Let me see. Is given. Yeah. So A4 is given on page 168, and the B32, and I think it's also show. It's also shown on some page in chapter 1. So I want you guys to take a look at by yourself. Yes, for B32 is shown on page 12. And for A4 is also shown on page 11. Yeah, so no matter which version we have, they all have LIM module, okay, which connects with all different components. Now, before we go to the details about each module, so let's talk about the hardware feature. So we mentioned before low power consumption. Yes. So it's really designed to consume power very little, because it uses CMOS technology, as I mentioned. Okay, low power consumption. Okay. So in this case, what is very ideal for the remote access. Okay, is ideal for the battery operated the application. Like you send robots which run 6080H12 on surface of Mars, so it works there by itself, and also it's very easy we can remotely access it. Well, for example, for the A4 version, in a single chip mode, after a while we talk about its operating mode. Even for A4 version, we may have different operating mode. If we assume A4 runs in a single chip mode, it only consumes 25 milliampere when running at 2 MHz. So when the frequency is 2 MHz, it only runs 25 milliampere. So it consumes very little power, and also it's high speed. Okay, because CPU is a 16-bit data processing unit. So in this case, it allows a wider range of allowable operands and 2 baud operations opcode, because each time we can send 16 bits of data. So speed is we simply say is double over the 68HC11. 68HC11 I mentioned is only 80 bits data. The CPU is only 80-bit data processing unit. So the data bus is also only 80-bit. So let's talk a little bit more about A4. Okay, let's talk a little bit more about A4. A4 is 1K RAM, as I mentioned, as I show here, it's 1K RAM. See? the RAM here we go is 1K byte, and is EEPROM is 4K bytes. That's why I call it A4 version. A4 here we go. Okay. The EEPROM is 4K. So for B32 is RAM is also 1K, but its EEPROM is B32 is what? It's 32 bytes. Is 32K, because that's why I call it B32. So the RAM size, no matter which version we talk about it, the same, always 1K RAM. Okay, that's more than enough. However, for the EEPROM, for the A4 version is 4K bytes. For B32 is 32K bytes. Here we mentioned. So 1K RAM for all variants, that's adequate for many applications. 4K bytes EEPROM for the A4 version. Okay. Now, I think everybody should be clear about the difference between the RAM and the EEPROM, right? Yeah, RAM's mainly like designed for us to store and access data values, so we can either read or write, like stack. Okay, like stack. For EEPROM, okay, of course, is not we cannot write any data to there, because it's mainly designed to store the programs on the microcontroller, like to store the machine code of the instructions. So we store there, and the user is not allowed to change them. Okay, because it's ROM. It's really only memory. We can only access them. We can only read. Okay, in this case, if you change the systems, if our program instruction, the whole system has been changed, then then the manufacturer, they can access them. Okay, then they can easily upgrade the instruction set like this. So it's quick and easier to update the program systems. So in addition to memories as 1K RAM and 4K EEPROM, and we have input and output systems. We have 8-channel 16-bit timer systems, and so we can configure each channel separately as input or the output. In other words, they are input-output configurable. Okay, so we have 16-bit timer as here. I just show you timer system here. They're right here. The timer system right here. Let me just show you here. Pretty much, let me use a different color to show you here. Pretty much like this. Excuse me. Right here, timer system right here. Okay, they're right here. Here we go. And we have 8 channel. Okay, we have 8 channel right here. See the channel from IOC 0 to IOC 7. Okay, this right here. There's 8 channels. The input output channel 0, input output channel 1. They're input output, so we can even change its channel configuration to be input output. That's why you see the direction of the channel here. The direction of the channel here we go. You see those? They are bidirectional. They're bidirectional. All of this. We have 8-bit channel. Okay, and it's 16 bits. So for each channel, because they are input output configurable, so we can configure each channel as input or output. That depends on our requirement. After a while, I will show you an example about how to do it. In addition, we have a 16-bit pulse accumulator counter used to count external events. Sometimes like when we design a robot which runs a 16/8/12. Here we go. Assume now it hit like a wall or hit something, hit a rock. We hope it count how many times it hit. If we assume it hit water for 3 times or more, then we may ask the robots to turn around like this. So sometimes we need to count the number. We need to count how many times we have experienced external events. So that's job done by the 16-bit pulse accumulator. So we need to accumulate how many times we have that events. So we also have an interrupt capability. Okay, I think we know this well. So that's a real-time interrupt capabilities. So in this case, when the normal operation of the 68H12 is interrupted, so the microcontroller have to suspend its normal operation. Okay, it's specified interval. Okay, how long you need to suspend. Okay, so we specify this. So you can stop this one, you do something else. So your normal operation is interrupted because we have some urgent things. Okay, that's pretty much about the interrupt. So all the microcontrollers should have this capability. Then for the communication systems, okay, as I mentioned, here we go. We have so the communication for the 68H12 is mainly about what? Is serial communications. So please be clear about this. So the communication system when it's done is what? A serial communication, not in parallel. Okay, not in parallel. Okay, yes, because we designed to have we design the microcontroller to work with external devices to control the operation of peripheral devices. Okay, yes, so communication issue is very important. So as I mentioned on a block diagram, here we go. We have two communication systems. Let me erase those. Here we go. They're pretty much here. They are right here, SPI and SCI. SPI is serial peripheral interface, and CI is what? Right here is the communication interface. So we have two different interfaces for communication system, for serial communication systems. One is SCI, one is SPI. SCI is a serial communication interface. Okay, we have its communication done is in the mode of asynchronized. It has two channels. For SPI is serial peripheral interface. Its communication is done in synchronized. Okay, a synchronized mode. So these two are different. So I want you guys to be clear about the synchronized communication and asynchronous communication. So for synchronous communication in general, so we share a common time clock. A common time clock signal is shared by both the sender and receiver. So like when we connect a hardware, when we connect an external device into a 68H12, okay, then the sending systems or the transmitter systems and the receiving systems, okay, they share a time clock. So at what particular time, both the sender and receiver then knows, okay, what's sent. So okay, so they know. So both the transmitter and receiver they're synchronized for data transmissions. So they know at what time, okay, which part data should arrive. The receiver knows this. Sender also knows this. They can synchronize. So we pretty much say they share time clock. Okay. Now for asynchronous, it's not. Okay. Both the sender and transmitter and receiver they do not share time clock. So in other words, okay, the receiver will not know at what time the sender will send. But if, in this case, how the sender and receiver they can get synchronized for data. Okay. The many based on the individual packets. Individual data packets already contains information about where this data comes from and what's the destination that the packets should go. So it's asynchronous. So it's asynchronous because they do not share time clock. So the packet itself, data packets itself already contains information where it's from, where it's to go. So when the receiver knows where it should go. So even though they do not share time clock, so they are not synchronized. Okay, but a data synchronization is done by the packet itself. So we have two interfaces, SPI and SCI. Now, if you go back to if you go back to our block diagram, we see this. Okay, we see this. Yeah, it's right here. See, we see this. Okay, SCI has two channels. It's this one, TX transmitter and receiver. Transmitter and receiver. Those two and those two. This is for SCI. So we have SCI 0, SCI serial communication interface 0, and serial communication interface 1. And for SPI, we have peripheral interface is only 1. Yeah, like this. They all communicate into the port S. Port S right here. This is port S. They communicate with port S. Okay, port S means what? Serial communications. So we have some other ports. We'll talk a little bit more in a while. Then, as I showed you, we also have A to D conversion. Here we got A to D conversion, A to D. Why we need A to D conversion? Because all the signals, okay, because the microcontroller only works with the digital signals. But it's possible we need a microcontroller to work with a device which can output only analog signal. Or when our microcontroller can export only a digital signal. However, external device we try to control can only receive signal the analog or can only process analog signal. In this case, we need to do A to D conversion or D to A conversion. That's pretty much done by the A to D conversion system of the 6080H12. Okay, we have an 8-channel, 8-bit A to D converter systems. But I show you here on block diagram here, the way on the top right here. This piece right here, you see right here, it's 8-channel. Here we see AN0, okay, AN0, okay, analog 0, and like 1 like this. A D conversion 0, 1, 2, 3, 4, 5, 6, 7. So we call it A D conversion. So it mainly work with the word port AD, port A to D. So this is the port that we receive signals from outside. The top several pins right here, mainly to input the voltage to make it work, and make sure each different subsystem, like those timer systems, and those what all require its own voltage. Okay, like this part on the left side has its own reference voltage. So that's pretty much an overview of the 6080H12 hardware. Now let's go to talk about its operation mode, okay, which is the second bullet. So given a 6080H12, okay, that depends on the user requirement. User can configure the microcontroller mode to run in different mode. So they're divided to have 8 different modes we can use. 8 modes we can use. And those modes are divided into a normal operating mode and special operating mode. Normal mode and special mode. So for user in general, we only deal with normal mode. Okay, and then we never touch a special mode. Okay, a special mode they're designed for special operation. They're not for a regular user. The design are mainly used for the factory testing and system development and debugging different things. But what's the main difference? What's the main difference between these two operating modes? When it's configured in to operate in normal mode, then some registers and some bits of registers are protected against accidental change. So in this case, what okay. Some important registers and some bits of information, okay, they are never allowed to change, even though accident happened for the operation of microcontroller. In comparison, a special mode, they are allowed to change. So if you configure microcontroller to run in a special operating mode, okay, then people allowed to have greater access, okay, to some part of data. But in general, okay, as a regular user, as we mainly runs 6080H12 as a regular user, but we don't deal with hardware, so we don't talk much about special operating mode. So we only focus on the normal operating mode. So how to configure a 6080H12 to run in a particular mode? Or in other words, how can we configure a 6080H12 to run in a normal operating mode? Okay, we have 3 pins. We have 3 pins. They're called what? They're called the background, mode B, and mode A. Those are hardware external pins. Okay, that what? That we can specify. We can specify its states. We can specify each bit to be 1 or 0. Okay, during a processor reset. When we reset, here we go. When we reset, okay, those pins already has value that will configure our 68H12 into a particular mode we have. Now, so we mentioned about what? We mentioned about the main difference between the normal mode and special mode. But even for normal mode, okay, we have different mode. Okay, we have like after a while we'll talk a little bit more. So even for the normal mode, we have 4 different modes. Okay, so what's the main difference between these 4 different modes in normal mode? In general, if we configure in different modes, then what? It will affect the configuration of memory and the bus. So when you configure your microcontroller to run in a particular operating mode, even in the normal mode, then its memory structure will be changed, or your memory mapped. Okay, your memory will be mapped in different ways, and including what? External buses. The bus operation, some port will change to for data transmission. Some port may be changed only handle data transmissions, or some port changed only handle address, and some port only to do what? For input output. Yeah, and like this. So that's pretty much about the mode. So what I'm going to do now is to show you where are these 3 pins, where are these 3 hardware external pins that when we reset the computer that will configure 68H12 into different modes. So let's go back to the block diagram I showed you a moment ago. They're right here. So let me clean this everything I already shown right here. Yes. Let me show you where are these pins. They're right here. Let me put let's show right here. Background pin right here, external pin right, this one. And the mode A and the mode B, they are these 2 pins. Okay, so these 3 external pins depends on the values 1 or 0. We determine which type of operating mode we run. So let me show you. So let me show you right here. This table shows us depends on what's the value of the 3 pins. The background D, okay, the mode A and the mode B. And we have here. And now in the new edition we changed to the mode C. For the background D here, we don't call it background. We don't call it background anymore. We simply call the mode C. Mode C. That's fine. We simply call the mode C. Yeah, but actually it's what? It's the same. It's the same. But we simply call it mode C. So here I show us depends on what's the value of those 3 pins. Okay, what mode we have. So it's right here because we have 3 pins. Okay, and the only value can be either 1 or 0. In this case, we have 8 different combinations. But I show you here. 8 different combinations. Right here, let me show you. When the mode C, this is B. Let me show. This is B here. This is B. This is A. This is C. Okay, let me show you here. Right here, when the mode C is 0, then we configure 68H12 into special mode. And when mode C is configured into 1, right here to 1, those, then we configure 68H12 runs in the normal operating mode. Okay. Then specifically, okay, because we will not talk much about a special mode. special mode right here, that depends on which special mode we have. Okay, this they are determined by the bits, by the external pins of mode A and mode B, by these two pins right here. Depends. Okay, we have special single chip mode, special expanded mode, narrow mode, special peripheral mode, special expanded mode, like this. Let's talk a little bit more about the normal mode. Okay, when these pins are 1, 0, 0, we have normal single chip mode. And then when we have 0, 1, we configure into normal expanded narrow mode. Then 1, 1, 0 is make it reserved, it's not used. And when we configure to 1, 1, 1, when we configure to those three, 1, 1, then we configure to run a normal expanded water mode. So we have normal expanded narrow mode and normal expanded water mode. So what's the main difference? So let me show you. Well, for example, let's talk about the port A. Where's port A? Port A, we can get back to the book, we can get back to the block diagram, we see where's port A. Port A, they are here. Those are port A. Those are port B. Those are port C. Those are port F. Those are port G. Those are port A. Those are port B. Okay. Those port A's, okay. Right here we see it has 80 pins. Okay. So what happens? So if we configure a 60ADH12 in normal single chip mode, in this mode, this way, 100, then what? The port A will become the general purpose input output port. Same for port B. Okay. But however, if we configure the microcontroller to run in normal expanded narrow mode, then okay, the pins from 8 to 15, those 80 bits to what will play as address, and the port what pins from 0 to 7 we run for transmission of data. But if we configure that what in port B, okay, 0 to 7, okay, they are used to serve to transmission for address. Like those, so they're different. Is when we configure in the normal single chip mode, they all serve as input output. But when we expand the expanded mode, then because we have much wider addresses, so we require some more addresses. Like this. Then when we configure the normal expanded water mode, it's pretty much same as normal expanded narrow mode. Now, if you go to a book on page 175, and then that table I show you here is pretty much it's similar to one I show you on this slide. It even tells us about depending on which mode we configure how the port C and the port D are used. I just want you guys to read it yourself. So when we configure it in a normal single chip mode, the port C and the port D are also served as the general purpose input output port. But when we configure it in a normal expanded narrow mode, the port C is to serve as data port, but port D is still served as general purpose input output port. But when we configure it in a normal expanded water mode, then Then port C and port D are only transmitted for data. But port B and port A, they can send addresses. Like those. So mainly to serve different requirements, different applications. So as I mentioned, in general, we only run 60ADH12 in normal mode. As a user, we didn't care about the special mode. So here, okay, I refresh. Okay, I refresh what we talk about. The different modes, the different 3 modes we have in the normal mode. So we have single chip mode, expanded mode, and narrow mode. So the main difference between expanded water mode, main difference between these two, okay, say in the expanded water mode, a data bus is 16 bits, and for the expanded narrow mode, data bus is 8 bits. That's why we simply see here we got this. We simply here in the WAD mode, in the WAD mode here, like this one. Okay, we set the address, right? Yes. With the data here, we got data runs can be address data here. With this. You see, if when we have normal expanded mode, okay, the port B only serves as address, but port B can also transmit data in expanded WAD mode because we transmit more data bits. We transmit more data. Because we have 16-bit data bus for the expanded WAD mode, and we have 80-bit data bus for the narrow mode. That's why one called narrow, one called wide. In the single chip mode, okay, it works according to whatever it is by default. We don't need to make any changes on this port. You see, in the single chip mode, all port A, B, and C, D they serve as general purpose input-output port, as shown on figure 5.6 on page 175 of book. If you turn to page 175, you see the table right there, and it shows us what's the port A and B and C and D. They all serve as the general purpose input-output port because everything is self-embedded single chip mode. So here I give you guys a little bit more explanations about them. So we see when it runs in the normal single chip mode, which means what? When the mode C is 1, when the mode C is 1, normal C is 1, let me change the blank color, and mode B is 0, mode A is 0, so we have 1, 0, 0. So we have no external addresses and data buses because it works by itself. It works alone, self-contained. Everything's done on a single chip. Okay, so all ports, okay, is used for general purpose input-output function. But when we configure it in normal expanded WAD mode, which is mode C is 1, C is 1, mode B is 1, mode A is also 1. Then external bus is presented as 16-bit data bus. Port A and B served as 16-bit address, and port C and D serves as 16-bit data. So in this case, it allows a much larger range of numerical operands. Okay, because this mode is designed for the 68H12 to work with a program which requires much more memory resources than is available on a normal single chip mode. That's why I call the WAD mode, expanded WAD mode. Address 16 bits, data at 16 bits. But in comparison, if you configure it run in normal expanded narrow mode, means what? It means we have the mode B to be 0. Then data bus changed to 8 bits. Address is still 16 bits. So the A and B used for a 16-bit address bus. Port C is used as a transmission of data. Okay. Now let me show you. Let me show you the pins, the hardware pins. So this slide I'll show you the A4 configuration in a 122 pins thin quad flat pack. So this is like a water. Everything for the A4 version is shown on a single chip. On single chip, we have 112 pins. Okay, but here I show you one. I'm sorry. Here I should change to 112, not a 122. 112 pins. Yeah, this is what I copied here is figure 5.7 of our textbook on page 177. Shows everything about the water has a single chip, very small size, a little bit larger than than thumb. Okay, a little bit larger than a thumbnail. Yes, here everything is shown here. So if you count all pins here, we start from here. This is pins 1 and 2, 3, and all go back this way. Come the last one, so 1, 12. Okay, those contains all communication ports, everything we have. Okay. So most of these pins, okay, they have two different functions. Okay, it depends on which mode do we configure. They either send data or address. Yeah, like this. So we call it 112 TQFP, thin quad flat pack. So this is what self-embedded, okay, 68H12 A4 version of microcontroller. You see, we have a lot of pins. There are 112 pins. Now we have so many pins. Okay, these pins can be roughly divided into the different groups. Some pins only to do some job, and while some other pins they do some other jobs. So those pins divided into the voltage pins. That's called what? The voltage supply pins. To what? To voltage pins that begin with V. And some other pins called what? The port pins that begin with P. We give names and then also name them. Then we have some other pins we call what? Miscellaneous pins. Okay, they mainly designed them what? To provide external signals for communication to 68H12. Okay, so if you look at some pins here, we go. We see right like those pins. Let me show here. Those pins here, VRH, VRH. Those pins here, we go. Those pins. They manage to supply voltage to the different subsystems. Those pins here, you see those pins. They only to give voltage. Why we have so many pins to voltage? Because the different subsystems of the 68H12 microcontroller require different amount of voltage. The voltage are even different. So we provide individual voltage to individual subsystems. So those started with V right here, they call the voltage pins or the voltage reference pins. Okay, so here I show you we have different reference voltage for different systems. We have a large number of pins that start with P right here. You see, okay, I show you here. So here I show you those with P's right here. They are port. Those with the PB4, PB0, PB1, PB2, like those pins right here. PC. The PC, the PC0, PC1, PC2, like those. And we have some other pins. We see a lot of PJs and PTs, and PS and PADs, and the PH, okay, and the PF right here, and PS. Those are manifold port. Okay, so the following P is what? The letter following P, okay, represent the function of the port. Because some pins, because some port they are for input data, some ports are some of them for port T, sometimes for port A, those. So we need to represent them. Okay, so when we and for example we have PT0. With PT0, let me make it. We have PT0. PT0, P means is a pin, T means for port T. The 0 means what? Is pin 0. It's first pin of port T. Okay, and those 8 pins, okay, for port T, they're named what? Numbered from 0 to 7. So that means what? That means if you have PT0, where's PT0? PT0 is right here. If you go back to our block diagram, port T, that's manifold port T. Right here, where's port T? We can simply see this port D right here, port H, port J right here, port E here we go. So where's the port T? Okay, port T right here. the manual to what? To communicate, manual to serve communication for timer systems, for timer system models. For T here we have the PT0, PT1, PT and PT7. So PT0 is first pin of port T, which is used to what? For communication for the timer system model. Same idea for other system models. Okay, we have some other pins. Okay, there are many to provide external signals. We can see all the rest pins. So that's pretty much about the pins, about hardware pins. So let's talk a little bit more about individual subsystems. So if you go back to the block diagram, as I just showed you, we have register blocks. Here we go. We have port systems, we have timing systems, we have memory systems, interrupt, time clock, and serial communication. For memory, we talk a lot more about memory when we go to the microcomputer 2 course. We talk a lot about memory designs, and and also we talk a lot about communication systems. So we will not discuss our memory systems. So we will focus on I think pretty much the first two. Okay, the first two, and when we have labs, we may use them. We focus on the first two subsystems, and they're mainly pretty much about the register block systems and the port systems. Port system is very important for communication. And for serial communication, I think they're pretty much easier. But so we have serial communication, and we have synchronous communication and asynchronous communication. And so we have course on communication systems. So the principles, it follows this series. So let's talk a little bit more about the register blocks. Now, when we mentioned about register, okay, we mentioned about when at the beginning of the semester, we mentioned that we have CPU registers and the memory registers. CPU registers, they are named like what? Accumulator A, accumulator B, index register, and like a CCR. Those are the well-known CPU registers. In addition, we have external registers. They are not inside the CPU, they are on memory. So we have a large number of this type of external registers. How many do we have? We have a large block. They consist of 512 bytes. It's half K. So out of 65,536 memory locations of the 68H12, about half K of them are considered to be registers. They're memory mapped. Why they're memory mapped? Because each register has address. Each of them has memory mapped address. So we have large collections of those registers. But what's the job? Why do we need such large number of registers? They're actually nothing but memory locations of memory. We need them to configure, okay, the 68H12 for specific tasks. So by using those registers, okay, we are allowed to change. We are allowed to what? To turn on or turn off a particular subsystems of the 68H12, and we can even change its configuration for a specific application. Like here we go. We have so many subsystems. We have timers. Right here, see, I show you. We have timer systems. We have time clock, interrupt, serial communication. All of them can be turned on or can be turned off. Depends on our need. So we can turn these systems on or off. We can even change its configuration for a specific application program by changing its corresponding, the corresponding registers. So where are those registers? They are out of here. They are out of this 512 memory byte registers in memory. Okay, so I mentioned here we go. When we say memory mapped register, that means what? Each register is nothing but a memory location. So it has addresses. So if we want to change its setting, we simply reset its value. How can we reset the value? We simply store a new value. How can we store? Okay, we can simply load the value into a particular CPU register, like accumulator A. Then we store this accumulator A value into what? Into this corresponding address. So that will change hardware operation setting. So we change hardware operation setting, like a turn off, or change its setting by changing its corresponding register in memory location. How? We load a new value into this register, then it's change its setting. So here I show you. So now in general, here we mentioned about we can turn on or turn off. We can turn on or turn off, okay, particular hardware subsystems. That's easy. In general, okay, we make the power on. We make the power on or power off bits of the corresponding register to be either 1 or 0. If it's 1, then we turn on. If it's 0, we turn off. That's easy. Sometimes we need to change the system for a specific application. How can we do that? In this case, we have to examine each individual bits of register to determine its setting. Then we use a store instruction. We load the defined value to it. So on page 178 and 179, we have example. The example tells us about how can we change the settings. So if you turn to page 178 and 179, yes, right here. So on page, right here we go. On page 78 and 79, we have an example. This example is what? Is to show us how can we turn on the A to D conversion systems. This system here, I show you this system. This system. How can we turn on this system? By turning on the power on bit of its corresponding register. So the A to D converter system right here, its corresponding register is called a A to D control register. Okay, so we do have such register on what? A memory location 0062. On our what? The memory location, the memory location whose address is 0062. That's a register. That's a memory mapped register. That register is called a A to D control 2 register. It's designed to change the setting of the what? Of the A to D conversion system. So we can make the what? We can make the leftmost bits. Okay, the bits what? The bit 7 to be 1, which will turn on the A to D conversion system. So it's very easy. So then what? In this case, what? We need to store a value 10000000 into this what? Into this address 0062. When we say, well, we save a value into this address at 0062, that means what? That means we change its setting to when we change the value at this location, which is what? The value of this register to be 10000000. So the leftmost bit is 1, which turn on, well, which will make the A to D conversion systems turn on. It's right here. If you take a look at the one on page 179, with the example right here. At the beginning, we use EQU, assembly directive. We equate A to D control register 2 to 0062. Why? Because 0062 is the address of this register. Because each register always have address. So we dedicated the memory location at 062 as A to D control register 2. So we equated them. Then what? Then, well, what? We load. Then what? Okay. We try to initialize the value. We're going to store to this location. So what? So we can turn on the A to D control the A to D converter system. So we equated 80. You see the second line on page 179. I mean, for this program, we equate what 80, which is 1000 into ATT initialization. So we initialize, okay, that's the value we hope to initialize. So we assign this 80 to ATT initialization. Then what? We load this value. We load this value. Here we go. We load this value to accumulate A. You see the third line, the third instruction here. We put pound sign because we use EQU. EQU is what? We never involve memory. So when you try to load this value at 0 into somewhere, okay, when you hope to load its corresponding value, numerical value, which is at 0 in somewhere, you had to put a pound sign in front of the label. Okay, right? Yes. So we put a pound sign in front of A to D INI. So that's going to load 80, this numerical value, into A. Then we store this value. So we store the 80 to what? To the A to D's control 2. Okay, that's what? That's the memory location at 0062. So we store the what? 10000000 at the memory location at 0062. So the memory location 0062 is actually this what? ATT control register 2. So when you make the leftmost bits to 1, that's going to, according to the design of microcontroller, that's going to turn on ATT conversion systems. Okay, like you see right here, you see how we use EQU, how we use load, and how we use store. We can change the setting of register, so it can change the configuration or turn on or turn off hardware subsystems. Here I show you right here. So I show you this. Same idea for other. Same idea for other registers and the corresponding subsystems. Here, make sure the ATT control 2, that's a name of the register. So we do have a register called the ATT control 2, which is the one which is located at 0062. In other words, what? The memory location whose address 0062 is nothing, is actually the ATT control register 2 register. So we can change the setting. So we can input a different value to there. So what? So in order to reconfigure, in order to configure our ATT conversion systems in different ways. So I think it's pretty much very easy to understand. So here I only show you one register, ATT control register 2. We have a large number of registers. Okay, here I show you we have how many? Half K, 512 byte. Well, with some registers, they take more than 1 byte. Okay, they may take 2 bytes, even more. So here I show you. Okay, here I show you. So we must specify here. I give you a little bit more explanation about what I just did. So we must specify the register location here and its initial contents for each and every register that's used in a given application. That's what we just did, right? We specify the location for the ATT control register 2 is 0062. That's how defined. We initialize its value to be at 0. Which is 10000000 to be in binary. So that's going to make what? The leftmost bits of this register to be 1, which turn on our ATT conversion system, which is to power up, as the comments on second instruction said, bits configuration to power up the conversion system. Now, in general, when we reset our microcontroller, then every register is configured to be what? To have default setting. Okay. Now also make sure, okay, those 512 bytes register blocks, they at the beginning at address 0000. Okay, that's why if you check the one I show you on page 179. Its address is 0062. It's so close to initial address as 0000. That's the one because we have half K. So this is one of them. Okay, you see, it's so close to 0000. Okay, now, however, we can remap it. We can remap to any 2K space out of memory. But however, when we move to a different location, okay, then what? Then when we move to a different location memory, however, for out of all these registers, the relative location still remain changed. So in other words, for all these 512 bytes memory locations, okay, we have a large number of registers. Okay, the orders all the same, no matter where you move to. So that's pretty much about registers. Now let's talk a little bit more about the port systems. As I just mentioned, okay, for the 6080X12, okay, it has extensive port systems designed to change data and control signals with external devices. So I mentioned it has a larger number of ports in comparison to the 6080HC11. 6080HC11 has much fewer port systems. Now this port, as I just mentioned, some port are designed as input input port or output port and configurable input output. Okay. Now in general, okay, these port addresses they specified use EQU. Okay, so now I'm trying to say the port systems they're working together with port registers. In general, we can change the configuration of port by changing different values of the port registers. Make sure we have a connection between port and port registers. So if you hope to change the port, some user here mentioned some ports they are configurable. You can configure either to be input or output. We can even configure individual bit of a port to be input and some other bits to be output. We can configure this port by configuring its corresponding registers. So we have port and port registers. Those port registers, where are they? They are the part of the 512 and registers. So in general, we use the help of EQU, as I show you the example, as well as I just show you for example on page 179. Same way we can change the setting of port registers so that the port systems can be configured in different way in a way that we want. So for bidirectional port, okay, with some port they only one direction, they only work for one direction. With some other port they are bidirectional, like port C. Here, if you go back to the block diagram, it's right here. Some port here they are only input. When some other ports they are they are bidirectional. Okay, they are bidirectional. For those ports, if they are bidirectional, then we can change its we can reconfigure them. We can configure them to be input like those. Let me show you. Like those ADT conversion ports. Like those, they're only incoming. See, they're only input. For those, they add external input or the output for those two, input or the output. For those and those, here we go. If they're designed to be bidirectional, then we can change individual bits to work. I mean, for specific application, to work as input pin or output pin. So what? So in other words, we can change the port channels to be input channel or the output channel by changing the corresponding register. So here I show you. In general, if you make its corresponding register pin to be 0, then you change its corresponding channel to operate as input channel. If you make its corresponding bits to be 1, then you change its channel to be output channel. So each bit within a port can be configured for input or for output. Look at those. Of course, we make this change. We make this configuration by setting a specific patterns of bits within the data direction. The data direction register is called DDR. Let me show you. Here we go. The DDR. So each port has a corresponding DDR. Okay, they're mainly designed for us to configure the port. So we can configure the port to be input port or to be output port, or to be input channel or to be output channel by programming or by setting a specific value of this data directional register. So here I mentioned all the input-output configurable ports have associated the data directional register. We call DDRX. Why we call DDRX? Because we have different ports. So all different ports have DDRs. Like for port T, we have DDRT. For port C, we have DDRC. That's why we use X here. So they are mainly used to configure the port as input or output. So let's take a look at the two examples on page 180 and 181. I will simply show you only one example shown on page 180. So turn to page 180. Turn to page 180. The example here shown on page 180 is to what? Is to show us how to configure the port C with 8 output pins. Okay, and then it's going to output the value 62. But now let me briefly only show you how to configure the port C. Okay, to have all the eight pins or the channels to serve as what? The output pins or to output the channels. In other words, let me show you how to configure the port C pins to output data by setting its corresponding data register for port C. Now the name of the port C data directional register here, DDRC. Let's call DDRC here. So we have DDRC. Because we'll talk about the data directional register for port C. We call DDRC. You see, at the beginning, as I showed you in example, for example, on page 179. So we used EQU. We equate DDRC as 0006. Okay. So what's that? That's the address of the data directional register C for port C. That's what another word. Memory location at 0006. Is dedicated for the data directional register for port C. So we equate 0006 to DDRC. Then, similar to the example I show you on this page, we initialize the value of DDRC initialization to be FF. Now, so we try to define DDRC initialization to be FF, which is 11111111. 111111 because 1 corresponds to output. We hope to change our port C all 8 pins to be what output data. In this case, you have to make its corresponding register bits, its corresponding data register bits to be all ones. So we make a FF to what? To DDRC. Then what happens? Then if you come to the third line, if you come to the fourth line, so we load this value. We load the FF, this value, into A. How we can load? So we place a pound sign ahead of the what is label. Because we use EQ, we don't reserve memory. If you reserve memory like RMB, then we don't need to place a pound sign ahead of DDRC INI. Here we use EQU. We label these values. Yeah, so we'll put pound sign. That's going to load FF to accumulator A. So now the value of accumulator A should be 11111111. Then we store this value 11111111 into a DDRC. What's DDRC? DDRC is actually nothing but the memory location 0006. That means what? We set in the values, okay, 8 bits value at memory location 0006 to be all 11111111. And this memory location actually serves as data directional register for port C. So that's going to change what? That's going to make configure. That's going to configure port C. That's going to make the 8 pins of port C all to output data. Okay, a similar idea for next 2 lines, but only the job to show these values. To output the 62. Similarly, for example, shown on page 181 is almost same. I just want you guys to take a look at the example by itself. Right here on page 181. It's okay. In this case, we configure all the pins to be input. Yeah, we configure the input port, and then it's going to read the values. When we try to configure the port C, all 8 pins to be input port pins, then make all values to be 0, 0. So that's why second line we try to equate the DDRC INI to be 0, 0, 0, 0, 0, 0, 0. That's going to make all the pins right here, to be input pins. So it's pretty much like that. So make sure we have a large number of registers. It's nothing but memory location. So each register has an address. So I mentioned that 68H12 has a large number of port systems. Okay, here I show you the many design for making it to be powerful to have communication with external devices. So we have a large number of port. Okay, we have port A from port A to H, port J like those. Those port A, B, C, D, and H and J, they're designed to be the general purpose input-output port. Okay, meaning to run in a single chip mode. Okay, but they can be, however, depending on other applications, if they configured to run in expanded mode, they can do some other jobs. Port S, I just mentioned here because it's mainly for serial communication. If you go back to the block diagram, they are right here. Right here, port S, right here. Those port S here. They're mainly for serial communications. And the port T is for timing, as I show you port T for timing, and port AD as I already show you here is mainly for ADD converter. Port ADD, okay. Port ADD here. They are here. So those PAD, port ADD, okay, mainly for conversions, okay, as the one I already show you. Okay, as I'll just show you. So in our book, they have they provide a very good discussion and explanation for each port on page 181 and 183. Talk about when we use them. So I want you guys read about yourself. So that's pretty much we prepared for this lecture. So we mainly focus on hardwares. And I just want you guys have an overview of hardware structures in addition to how to program them. And we already spend a long time learning how to program, but it's always good that we have quite a good understanding about the hardware structures and what do we have, and when we say is operating mode, what it means. When we say about the pins, okay, we have an idea about what those pins for, what are the other pins for. Also have an idea about registers and blocks. Those two, they work together. They work very closely. So this is pretty much what we prepared for this lecture about hardware.